Welcome back, class. So today I want to continue on with our discussion of Chapter 7 and introduce a concept known as enthalpy. So enthalpy is a thermodynamic concept that is really the heat, or Q, of a reaction that is held at constant pressure. So the constant pressure here is the key. So the enthalpy of reaction, or more importantly, the enthalpy change, right? Because in all of these, we're interested in changes, right? What happens at the beginning and the end of some physical or chemical process, right? So we have the change in enthalpy, right? And enthalpy is abbreviated by H, capital H, so the delta H is the heat involved in that change when that change is done under constant pressure conditions. So why is this useful? Well, remember that delta enthalpy can, in a form of equation, can be defined as, right, the change in energy plus P delta V work. So this is the definition of delta H. So it's the sum of the internal energy, or the energy, times PV, or P delta V. Now, if we think about some of the ideas that we've talked about, if pressure is constant, right? And let's say, as we talked about before, we have reactions that don't change volume, right? That don't have a change in volume. So if delta V is essentially equal to 0, then delta H is simply equal to delta E. So for the vast majority of reactions and process that we look at, the enthalpy is essentially the same as the energy change, right? So we've been focusing on calculating the change in energy here, focusing on the heat, but for large swaths of reactions, the enthalpy is very closely related to the change in energy. Now, so that means the energy, right, is equal to, enthalpy is equal to Q, right? So in a previous section, we saw that the change in energy of the reaction was equal to Q, right? Because no work was done. Right? If no work is being done, then that also means that the enthalpy is equal to Q, but at constant pressure, right? So the big difference here is the constant pressure idea. So enthalpy and energy are similar, sometimes very close, right? The differences are going to be the biggest when we produce large quantities of gas, because we start producing large quantities of gas, then the pressure is no longer constant, right? And so the enthalpy, to hold it at constant pressure, it means the enthalpy is going to be different than the energy change. So we tend not to deal with those kinds of reactions, right? And most reactions don't involve production of large quantities of gas. Now, we look at reactions or changes, whether they be physical or chemical, based on the value of the enthalpy change. And we label these as exothermic and endothermic. So an exothermic reaction, and you may have heard of these before, is when the enthalpy change is negative. Now, you may have not heard that, but you've probably maybe heard of exothermic reactions as reactions where heat is released, right? So these are reactions that have a negative value of Q, right? The system is releasing heat. That means, since enthalpy is equal to Q, that means these will also have negative delta H's of the system or the reaction. And that means endothermic reactions are the opposite, right? This is where heat is absorbed by the system, where we have a positive Q, and that means we will have a positive change in the enthalpy of the reaction. Now, we should also note that enthalpy is an extensive process, meaning it changes with the amount. So when we list enthalpies of reaction, the way we typically do it is we list it not per mole, but per balanced equation. So, for example, if we have this combustion of propane here, 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of CO2 and 4 moles of water. For this change, 2,044 kilojoules is released. Now, in this case, that is the amount released for every 1 mole of propane burned. Now, if you have a reaction where the coefficient is 2 here, then it would be the amount for every 2 moles or 3 moles or whatever the coefficients here. So this is the amount released for this reaction. So if we wanted to say double this, right? We wanted to know how much is released for 2 moles. Well, then we could double this. If we wanted to know how much for a half a mole, well, cut this in half. So this provides a ratio that we can use if we know what the balanced equation is to calculate for any amount. Because we know what it is for the balanced equation, now we can use this to find for any amount. So let's do an example of that. Let's say 500 grams of propane are reacted. Well, the first thing, of course, that we need to know is 500 grams. We need to know this in terms of moles, right? Because we're basing this on a balanced equation, which is based in moles. And so 500 grams. Propane has a mass of 44.11 grams per mole, or 44.08, kind of depends on, somewhere around 44.11, depending on exactly the molar masses that you use. Of C3H8. And so that gives me 11.34 moles of C3H8. So if I know from here that I have 11.34 moles of propane, and I know that based on the balanced equation, for every 1 mole of propane, I release 2,044 kilojoules. And that means for 11.34 moles, I'm going to release 23,169.3 kilojoules, or putting it in proper significant figures, right? So we have 3 significant figures here in our mass, or we can sort of make the conclusion that we have 3 significant figures here. So we're going to round this to 3 figures, so that's 2, 3, 1. The 6 rounds that up. So 2.32 times 10 to the, we got 1, 2, 3, 4 kilojoules. So if I burn 500 grams of propane, that's the amount that I'm going to give off, right? Now, again, the negative sign, the key there is telling me that it's energy released, right? It's energy given off, right? So I'm going to release 2.32 times 10 to the 4th kilojoules of heat here, or my enthalpy change, right? Will be 2.32 times 10 to the 4th kilojoules. Okay, so let's dive just a little bit more into these endothermic versus exothermic reactions. So let's start with endothermic. So remember, right, endothermic, right, positive Q, positive enthalpy change of the system or the reaction. So if we think of this, if we look at sort of a graphical way to look at this, and we look at the energy, right, the potential energy over the course of the reaction. So if we start here with our reactants and we compare them to our products, right, we're going to go up, right, because we need this change to be positive, right? So if we take the products minus the reactants, right, it has to be a positive value because, right, we're gaining heat, right? We're gaining thermal energy over the course of the change. Or in other words, right, it's warming up, right? And so what we see with endothermic reactions is that the system itself is absorbing heat. So what are some examples here? Well, chemical cold pack. Now this one's sometimes tricky because we say, oh, it gets cold, but remember, the surroundings gets cold. Right? So the reaction that's actually occurring, or the change that's occurring inside that chemical cold pack, is giving off, is absorbing heat from the surroundings in order to occur. So an endothermic reaction, the system for that change to occur has to absorb or pull in heat from the surroundings. That's going to cause the surroundings to drop in temperature, right? So the surroundings, right, will have a negative Q. Other examples of endothermic processes include things like photosynthesis, cooking an egg, sweat evaporating, right? Notice, remember how your skin gets cool when the sweat evaporates, right? So in order for that evaporation to occur, for that sweat to go from liquid to gas, it has to absorb heat from your skin, cooling your skin down. Right? So we get that evaporative cooling, right, of your skin. We talked about melting ice. Right? When we dissolve something, that's an endothermic change, right? Dissolving we have to absorb energy, or energy is required when something dissolves, because if we remember, when we dissolve something, like say we dissolve an ionic compound, we have to break that crystal structure apart. That takes energy. And so that energy comes from absorbing heat from the surroundings. And so dissolving things will require energy, right? So, in other words, we're absorbing energy over the course of the reaction. So our products end up with more potential energy than our reactants. So endothermic. Exothermic. These are, of course, just the opposite. And these are things that we're usually more familiar with. So exothermic reactions have a negative Q or a negative delta H of the system. So this means the system is losing energy, right? We're going from reactants that have a higher potential energy to products that have a lower potential energy. And that difference, right, is given off to the surroundings, right? And that's what we measure here as the negative delta H or the negative Q. So examples of this, anything that burns, the cellular respiration. So in the body we have both endothermic, or in living organisms we have both examples of endothermic like photosynthesis, or exothermic cellular respiration. Thermite reaction, right, which is here. This is the very exothermic reaction. We have those phase changes, right? So whereas evaporation and melting were endothermic, condensing and freezing are exothermic, right? So when we condense something, when it goes from a gas to a liquid, or a liquid to a solid, we have to lose thermal energy in order to go from a more energetic phase, a gas, where we have more motion, to where we have less movement. Less movement, we have more movement in the liquid, less movement in the solid. In order to make those changes, right, we have to lose some of our potential energy. Or what we typically see is we have to cool things down to make those changes occur. Okay. So exothermic. The key is, remembering these values, right? So the system, it's always the system that we think about. So endothermic, the system gains potential energy, has a positive change. Exothermic, the system loses potential energy. We have a negative change.